Example number 2. Prove that the equation x cubed plus x minus 1 equal to 0 has exactly one real root. For this problem, we will use two theorems to prove. The first one we will use intermediate value theorem, and the second one we will use the Euler theorem. And for the intermediate value theorem, let me show you the book. That is in section 1.8. Here, this is section 1.8, and that is the theorem number 10. So we had that in the test. Okay, so this is the theorem that I just copy and paste. And for this theorem, we can conclude that there exists a number c in AB such that f of c equal to n. So this is mean that the function f has a root c. Okay, so we can use that theorem to show this function has a one real root, and exactly one real root. The word exactly, we will use the Euler theorem to prove. So we did not learn how to prove exactly before yet. Okay, so let's begin. So remember right here, we will have this is f of x. This will be our n. Now we will choose a and b. So let's look at a and b in the interval 0 and 1. Okay, so suppose that based on the theorem, suppose that f is continuous on closed interval a comma b. So the function f of x is equal to x cubed plus x minus 1 is continuous on the closed interval ab. This is true, right? Because f of x is a polynomial, so it is continuous on the whole number line. So AB is a part of it. So of course, f of x will be continuous on a comma b, closed interval. And then we let n to be between f of 8 and f of b. So let's find f of 8 first. So f of 8 is 0. So if we plug in the 0, we will get negative 1. And f of b is f of 1 is equal to 1. So we have a number n. The number n in this case is 0. This is between negative 1 and 1. So by the intermediate value theorem, we can say that f of x has one root. Or this is the same thing as has a solution. Or you can say that there exists a number c in the open a comma b such that f of c equal to n. So this is the same meaning as saying that f of x has a root. And now to prove it is exactly one real root, then we will use the Euler theorem. Again, our function f of x is x cubed plus x minus 1. So we will assume the three hypothesis is correct, is right. So what happened to the first one? F is continuous, so yes, right? For some interval a comma b, from closed interval a comma b, f is differentiable. This is yes, because f of x is a polynomial. Then we will, number 3, we will suppose that we do by contradiction. Okay, we're going to suppose that a and b are the roots. And because it's the roots, that means the solution, then we will have f of a equal to f of b. So we are assuming 3 is true. Okay, so we assume that we have two roots and it satisfies number 3. Then by the Euler's theorem, we have the conclusion is here. Then there exists a number C in the open interval a comma b such that f prime of c equal to 0. But now let's calculate f prime of x from our problem. So that would be, this is f of x, right? This f of x is given. So then we will take the derivative, the first derivative, so we will get 3x squared plus 1. But what happened to this function, the f prime function, is this is never 0. Why? Because any value that you plug in the x, when you square, is always positive. And then you have 3 multiplied positive, so you get 3 something some number plus 1, so it's this, the whole thing is positive. And we know that it's greater than 1, okay, because this is always positive. At 1, the lowest number will be 0 for the x, yeah, plus 1, so you will have the answer is 1 is the minimum number for 3x squared plus 1. So when it's greater than 1 for all value of x, so this is contradiction, because we just conclude that f prime of c for some c value will be equal to 0. Now we look and it is not 0. It's strictly greater than 1. Okay, so we have the contradiction right there. Contradiction. So we cannot have two roots, and we just have exactly one real root.